Hello. Welcome, one viewer. It's Ethernet bedtime story again, and today we're going to start with Ethernet flow control, which finally we're getting into something fairly interesting with Ethernet. Up till now, it's been a history lesson combined with like basic network engineering stuff, so it's been a little bit dry. Not as dry as it could have been, I guess. We're not reading Cisco Press, but still, it's good to get to this more interesting part. So I'm just going to kick it off with flow control here. Ethernet flow control. Now I think, get to this in the last stream, but first that was on RPAN. Second, like, I don't remember a whole lot about flow control. I have to read things like 10 times to remember everything. So here we are, reading it again. Okay, Ethernet flow control. Settle in, get comfy, it's time to fall asleep. Ethernet flow control is a mechanism that allows an interface or switch port to send a signal requesting a short pause in frame transmission. At the time that this feature was developed, vendors were implementing various approaches to controlling Ethernet frame transmission in an attempt to manage limited switch and interface resources on busy networks. To provide a vendor-neutral way to signal a request for a brief pause in frame transmission, an explicit flow control message is provided by the optional MAC control and pause specifications in the 802.3x full duplex supplement. So it's optional, but we can do it, and that makes us vendor neutral, so that's nice. Today, switch and interface resources are no longer as limited as they once were. And while Ethernet flow control is implemented by vendors, it's not widely used for its original purpose. Instead, you'll find pause-based flow control used in data center switch implementations, for example, to provide quality of service for file storage data flows. So that's interesting. I don't really understand totally how that works, but I don't know anything about storage, so that makes sense. The optional MAC control portion of the 802.3x supplement provides a mechanism for real-time control and manipulation of the frame transmission and reception process in an Ethernet station. In normal Ethernet operation, the media access control, or MAC protocol, defines how to go about transmitting and receiving frames. In the Ethernet flow control system, the MAC control protocol provides mechanisms to control when Ethernet frames are sent out. Okay, so all of this kind of lines up already with like CCNA level stuff from what I've seen. We know like a tiny bit about MAC control protocol from the CCNA, but not a whole lot in detail, so this is interesting. Okay, to recap this last paragraph because my brain was wrapping around it. So normally with Ethernet, just typical operation, MAC protocol defines just how you're going to transmit and receive frames. Bam, that's it. And Ethernet flow control. So this is something we're setting apart from normal Ethernet operation, I guess, is Ethernet flow control. And that's where the MAC control protocol provides mechanisms to control when the Ethernet frames are sent. So normal Ethernet operation, we have control and manipulation. No, I'm sorry. See, it's not even absorbing yet. This is how much I can't pay attention. So normal Ethernet operation, we're talking about just transmitting, receiving frames. That's what MAC protocol does. But when we're talking about flow control with Ethernet, that protocol actually allows you to control when the frames are sent. So how to transmit and receive in normal operation versus flow control when the frames are sent, you can control that. I don't know why it's taking me so long to understand it, but I think I got it. All right. MAC control system provides a way for the station to receive a MAC control frame and act upon it. The operation of the MAC control system is transparent to the normal media access control functions in a station. MAC control is not used for non-real-time functions, such as configuring interfaces, that are handled by network management mechanisms. Instead, actually, I'm going to read that again. MAC control is not used for non-real-time functions, such as configuring interfaces. Okay, so that apparently doesn't qualify as a real-time function. Instead, MAC control is designed to allow stations to interact in real time to control the flow of traffic. The specification allows for new functions beyond flow control to be added in the future. Okay. Okay, so real time, we're talking about right now at this very nanosecond, we're controlling it as it's happening. That's real time function. Configuring interfaces is not that kind of function. Okay, so MAC control is not used for non-real time functions. It's only used for real time. Okay. So normally, again, when we're not talking about flow control, Ethernet just allows you to transmit, receive frames. It defines how that happens. Normal function of Ethernet. But when you're using flow control, it actually allows you to control when the frames are sent. So it's that real time sort of thing when you're talking. When are the frames sent? Well, it just says when they're sent, not received. I was about to say when they're sent and received. I mean, it's kind of the same thing, right? In a way. Yeah, okay. Okay, so we have the potential also, besides interacting in real time, controlling the flow of traffic in sort of a reactive way, it sounds like. We also have room still in 802.3x to actually have new functions defined, potentially, that are not necessarily flow control. So, cool. MAC control frames are identified with a type value of 0 by... And again, I should have asked this on Twitter like a million years ago. I don't know how you're supposed to pronounce hex things. Hex numbers. I'm literally going to tweet that right now. Nobody's watching. No one cares, right? Okay, let's see. Tweeting, how the fuck are you supposed to pronounce hex values? Or if someone knows, please tell me. Someone who might be watching this stream. If you haven't fallen asleep yet, let me know. Because in my head, you know how you just like are reading something for the first time, or you don't say it out loud very much, so you're just in your brain, like in my brain, this hex value, I want to read it out as it's written, right? 0 by 8808, but I'm pretty sure that's not how you're supposed to do it. Oh, I'm asking how you're supposed to pronounce, like if you see in the text over here, we have the hex value, this hex value. I'm asking how the fuck you're supposed to pronounce hex values because no one has taught me yet, and I have not. I've been too lazy to Google it, so it's really my fault, but here we are, live on stream. Hello, welcome to Storytime. Thank you for joining me. Hex 8808. Really? That's how you're supposed to pronounce it? That sounds pretty cool. I like it. As someone who really typos bother me a lot, and pronouncing things incorrectly bothers me a lot, even though I'll do it a lot with network concepts, but when I know better, I know better. So thank you. Okay, so we have somebody saying you're supposed to say hex 8808, or somebody else is saying that they usually say individual numbers and letters, but we don't know. Oh, all right, Javier. I was only at the Cisco TAC for about 18 years, and I always said it like that, but what do I know? All right, we have Cisco TAC in the room. I guess I'll believe Cisco TAC. Thank you, Javier. I appreciate it. Okay, so we're calling it Hex 8808. And I did tweet that question out, so you can also go correct me if you want to on Twitter. Just search Track at Pacer, you'll find me. I'm just gonna leave it up, but no, Javier, I'm making fun of you, but it's not. I did not take it seriously. Don't worry. I love it. Please keep correcting me. Keep making jokes. I love it. Okay, back to this. Yeah, another note. I always say, in all seriousness, if you're an expert or you know more than me about anything, And I mean it, anything. That's probably everyone who is viewing right now or has ever viewed my streams. If you know more than me about anything, please correct me or lecture me in the comments. Like if it really bothers me, I just like won't read it all or whatever. Like it doesn't matter, but I'd love to get the lecture and I'll try to read it out loud for viewers too or for future people like watching the recording, right? Because I'm here to learn. I'm not here to like show off, okay? Despite what it may seem like, you know. Okay, so we're back at it. Let me just start back at this like first paragraph, right? Mat control frames are identified with a type value of hex 8808. A station equipped with optional MAC control receives all frames using the normal Ethernet MAC functions and then passes the frames to the MAC control software for interpretation. Okay, if the frame contains the hex value hex 8808 in the type field, then the MAC control function reads the frame looking for MAC control operation codes carried in the data field. If the frame doesn't contain 8808 value in the type field, then MAC control takes no action and the frame is passed along to the normal frame reception software on the station. Okay. A station equipped with optional MAC control receives all frames using the normal Ethernet. Okay, so our station receives all the frames we're getting. No difference between them, the normal stuff, and MAC control. But it's always going to be looking out, I guess, for that hex value of 8808. And if it sees it, then it's going to actually look deeper, I guess. It reads the actual frame. Maybe it's not reading the frame. So many questions about how, you know, once you start like digging into stuff, you just can't stop, right? So like, okay, is it reading every frame or is it only reading them if it sees like specific hex values that, you know, trigger whatever, right, in the software? Okay, so we'll just leave it at, we see hex 8808 in the type field, and we're going to look for MAC control operation codes in the data field if we see that specific code in the type field. Otherwise, we just pass along normal frame reception software on the station, whatever the fuck that is. Okay, MAC control frames contain opcodes in the data field of the frame. The frame size is fixed at the minimum frame size allowed in the standard with 46 bytes in the data field. The opcode is contained in the first 2 bytes of the data field. There is no reliable transport mechanism, so MAC control must be able to deal with the fact that MAC control frames may be lost, discarded, damaged, or delayed. Okay, cool. Here's what I learned at the TAC all that time. I couldn't have done my job without Google. Or Alta Vista? Or Alta Vista when you started? You started and Alta Vista was a thing? Wow. Yeah. Okay. I don't mean to age you. I'm so sorry, but I haven't heard of I haven't thought about Alta Vista for a very long time. You kind of forget about it. I wonder what happened to Alta. Obviously it's not around anymore, I guess, but like I wonder what happened. Did it just get like absorbed by Google? So curious. What if I know less than you about everything? Then stick around if you wanna. I'm literally just learning out of a book, so that's why like I'm so sorry. I am not the most engaging person to teach you stuff. But I am giving you a free copy of a book, which I bought legally. I bought 2 copies of this book. I bought one that is the PDF right here, and I bought the other one, which is a physical copy, which I don't have here because actually the PDF version is like the 2nd edition, and then the hard copy that I bought stupidly is like 1st edition, so it's super out of date and old, the 1st edition. So Alta Vista was a series of alpha computers at Mae West in the Bay Area. It was cool to see basic internet infrastructure like that. Yeah, I bet that was so cool, because I bet that was so cool back when the internet was turning into a thing. I bet that was so cool to work in this field. And here we are where I technically left off last time. Pause operation. I'm pretty interested in this, so if it lets me down, then I'm gonna be devastated. Okay, the pause system of flow control on full duplex link segments, originally defined in 802.3x, uses mat control frames to carry the pause commands. The mat control opcode for a pause command is hex 0001. A station that receives a mat control frame with this opcode in the first 2 bytes of the data field knows that the control frame is being used to implement the pause operation for the purpose. Okay, wait, so where are we putting that? Okay, it's an opcode, so it's going to be in the data field. So this frame would look like in the type field hex 8808, and then as the device reads further into the frame in the data field at the first 2 bytes, that is our opcode. So that's going to be 0001. Okay. So that's how we know we're using pause operation for the purpose of providing flow control on a full duplex link segment. Full duplex. Only stations configured for full duplex operation may send pause frames. Okay. Pause is not an acronym. Instead, pause is written in uppercase letters to indicate that the word is formally defined, is a formally defined function in the mat control standard. This is common practice for formally defined words and phrases in the standard. Okay, so basically it's capitalized because it looks cool. That's fine, whatever. We do a lot of stuff for that reason. When a station equipped with mat control wishes to send a pause command, it sends a pause frame to the 48-bit destination multicast address of 0180C2000001. Okay. All right, so we have an actual destination multicast address for a pause command. I'm just reading back for just a second. So, am I correct? We have a pause frame, and it looks like the pause frame looks like in the type fields of the frame, hex 8808. In the data fields, first 2 bytes are our hex 0001. If it's I guess if it's a pause, specifically if it's a pause operation, it's not always going to be a pause operation if we're talking about flow control. Well, I don't know. Is that the only command that you'd be using in flow control? That's all we've talked about so far. But then we're also, if it is a pause command, we're also going to have a destination multicast address of this guy right here. This particular multicast address has been reserved for use in pause frames. Having a well-known multicast address simplifies the flow control process by making it unnecessary for a station at one end of the link to discover and store the address of the station at the other end of the link. Okay. Getting rid of ARP-like things. Another advantage of using this multicast address arises from the use of flow control on full duplex segments between switches. The particular multicast address used was selected from a range of addresses reserved by the IEEE 802.1d standard, which specifies basic Ethernet switch or bridge operation. Normally, a frame with a multicast destination address that's sent to a switch will be forwarded out all other ports of the switch. However, this range of multicast addresses is special. They will not be forwarded by an 802.1d compliant switch. Instead, frames sent to these addresses are understood by the switch to be frames meant to be acted upon within the switch. A station sending a pause frame to the special multicast address includes not only the pause opcode, but also the period of pause time being requested in the form of a 2-byte integer. Oh yeah, I did do this last time. This is fun. All right, here's math. The number contains the length of time for which the receiving station is requested to stop transmitting data. The pause time is measured in units of pause quanta, where each unit is equal to 512 bit times. And when I was reading this earlier, I definitely had to look up what the fuck a bit time is. And I'm gonna look it up again because it's a little bit weird. but really cool. So bit time is a concept defined as the time it takes for one bit to be ejected from a network interface controller or NIC operating at a predefined standard speed. The time is measured between the time the LLC sublayer, which we're familiar with now, receives the instruction from the operating system until the bit actually leaves the NIC. So from first instruction received to bit out of the NIC. The bit time has nothing to do with the time it takes for a bit to travel on the network medium, but has to do with the internals of the NIC. Pretty interesting. So you can actually calculate bit time in real human time. Bit time is basically 1 over the NIC speed. So for a 10 megabit per second NIC, for example, you would use bit time equals 1 divided by, and this I'm literally just reading from Wikipedia, this formula, because I don't completely understand it, and I meant to look it up, but as with everything, I didn't. So bit time is 1 divided by, in parentheses, 10 times 10 to the 6th. 10 to the 6th, so 6 zeros. Something to do with it being megabits, I'm sure. Yeah, okay, so number of bits. 10 times. Okay, so that equals 10 to the negative 7th, which is the same apparently as 100. I'm not a mathematician, all right? I'm sorry. I was an English literature major. Okay, 100 times 10 to the negative 9th is the same as 10 to the negative 7th, and that is the same ultimately as 100 nanoseconds. So, all of that is to say bit time is 1 divided by the NIC speed. So if we're coming back to this, our pause time, when we're sending a request to pause with Ethernet flow control, the pause time, the amount of time to actually, I guess, pause sending data, is measured in units of pause quanta, which is 512 bit times, which means you can take 1 divided by the speed of your NIC, right? And then multiply it by 512. And that is 1 pause quanta. I'll say it again for my brain and yours. A single unit of pause quanta is 512 times, in parentheses if you want to, 1 divided by your NIC speed. So the example Wikipedia so nicely gives us is if it's a 10 megabit per second NIC, then it's 100 nanoseconds is your bit time. So 100 nanoseconds times 512. So what, 51,200 nanoseconds? Yeah, anyway. No, I can do math. Oh, God. I'm going to cut this out of the recording. I'm going to edit this video. Anyway, it's 512 times 100, right? That's more than what I just said. That's your unit, that's your real time. I don't know how you would see. It'd be really cool to like try wire sharking some like Ethernet flow control shit going on, but I don't even know how you configure this or try to look at it at all or find out when it's happening. Maybe we will find this out later. Math is not fun. No. Okay. So here we have a diagram of a pause frame. Cool. So we have our data field as we normally do in any frame. First 2 bytes are our control opcode. So if we're sending a pause frame, it's going to be hex 1. And then we're going to have the next 2 bytes, if it is pause frame, dedicated to the pause time. So here we have a pause time of 2 in hex. And that's it. So that apparently means that we are not going to transmit. We're pausing for a period of time equal to two pause quantas. So that would be equal to 1024 bit times, since each pause quanta is the same as 512 bit times. So yeah, I'm not even gonna try to do that math on the fly if we're talking 10 megabit per second link, but I'm sure you can figure it out. Cool. Okay, so here, yeah, this is actually a nice little diagram because we have our destination multicast as they said it would be defined, right? 0180 C2 quad 001. And then we've got 8808 as our control type in the type fields. And then in our data field, we've got our pause opcode, excuse me, and then the pause time defined right after that. Fun. By using MAC control frames to send pause requests, a station at one end of a full duplex link can request the station at the other end of the link to stop transmitting frames for a period of time. This provides real-time flow control between switches or between a switch and a server that are equipped with the optional MAC control software and connected by a full duplex link. All right. Now here's the part where I kind of skim over it for a second because we're talking about high-level protocols and Ethernet frames, and I am going to skip some of the parts of this that go over basic CCNA concepts simply because learning is good and refreshing is good, but I want to get through this book and not forever, and so I probably don't need to look at everything I already know. This is cool. The process of identifying which high-level network protocol data is being carried in the data field of an Ethernet frame is called multiplexing. Identifying which high-level network protocol data is being carried in a frame, multiplexing. In multiplexing, multiple sources of information can be carried over a single system. In this case, multiple high-level protocols can be sent over the same Ethernet system in separate Ethernet frames. Okay. Do we want to read this? I was about to sneeze for a second. It's gone. Okay. All right. We'll just keep going because this is interesting. The original system for multiplexing for Ethernet is based on using the type field in the Ethernet frame. For example, the high-level protocol software on a computer can create a packet of IP data and then hand the packet to software that understands how to create Ethernet frames with type fields. The software inserts a hexadecimal value into the type field of the frame. This value corresponds to the type of high-level protocol being carried by the frame. It then hands the data to the interface driver software for transmission over the Ethernet. I'm going to read this whole paragraph again so it will soak into my stupid brain. And I also find it just super fascinating because this is the kind of like deep down level stuff that I really wanted to get into in this book, and it's not disappointing now. Okay, starting over again. The original system of multiplexing for Ethernet is based on using the type field in the Ethernet frame. For example, the high-level protocol software on a computer can create a packet of IP data and then hand the packet to software that understands how to create Ethernet frames with type fields. The software inserts a hexadecimal value into the type field of the frame. This value corresponds to the type of high-level protocol being carried by the frame. It then hands the data to the interface driver software for transmission over the internet. Cool. So this is encapsulating a packet is what it sounds like in a frame. So we have our high-level protocol software on your computer or whatever. It creates its own little packet of IP data, and then it sends it to software that specifically knows how to create frames. That software encapsulates it in a frame, adds the type field because I guess it knows like what the high-level protocol is. It's like a translation. And it inserts that hexadecimal value into the type field of the frame to define what high-level protocol is going to be in there. And then it gives the data to the next guy in the chain, the interface driver software, which is what actually transmits it over the Ethernet medium, which is juicy details. Okay. The Ethernet interface driver software deals with the details of interacting with the Ethernet interface to send the frame over the Ethernet channel. When carrying IP packets, the type field will be assigned the hexadecimal value 0800. Okay, IP packets. The receiving station then uses the value in the type field to identify the protocol data being carried, and thus demultiplex the received frame. So we're multiplexing at the origin, at the source, and we're sending and demultiplexing at the destination. Okay. Each layer of the network system is substantially independent from the other layers. Encapsulating the data being passed between layers helps maintain independence between the layers, making it possible for a complex system of network software to be broken down into more manageable chunks. By providing standardized operating system interfaces to the network programmers, the complexity of each network layer is effectively hidden from view. The programmer is free to write software that hands the completed high-level protocol packet to the appropriate computer system software interface. The details of placing the protocol packet into the data field of an Ethernet frame are automatically dealt with. In this way, an IP-based application and the IP software itself can function without major changes, regardless of which physical network system the computer happens to be attached to. Very cool. Hello, welcome. Welcome to the stream. Come fall asleep with us to the sound of me reading you a book about Ethernet. Things are made somewhat more complex because of the presence of two methods of identifying data in a frame. One using a type field to identify the data, and one using an IEEE 802.2 Logical Link Control, or LLC, standard. Okay, so we have two methods of identifying the data. We can either use that type field, as we talked about before, or the LLC can actually do something. However, many network drivers are capable of identifying and dealing with multiple frame formats. I would assume today, this book is a little bit stale. It's a little behind the times. I would assume today we have a lot of software that can do that on its own. Okay, now we're going to talk about LLC. As we've seen, the value of the identifier in the length/type field determines which way the field is being used. When used as a length field, the task of identifying the type of high-level protocol being carried in the frame is moved to the 802.2 LLC fields carried in the first few bytes of the data field. So this is length. Length LLC. Easy to remember. Okay, so I guess up here, prior to this, we were talking about what happens when we're using the type field, but now we're talking about using it as the length field instead of the type. It's the same field, I think, just called something different depending on how you're using it. So, okay. Here's our little figure. It shows an IEEE 802.2 LLC Protocol Data Unit, or PDU. The LLC PDU contains a Destination Service Access Point, or DSAP, that's awesome, which identifies the high-level protocol that the data in the frame is intended for, much like the type field does. After a Source Service Access Point, or SAP, I guess, SAP, and some control data, the actual user data, or the data that makes up the high-level protocol packet, follows the LLC fields. I'm going to read that again because that did not absorb too many acronyms happening. Okay, so this is an LLC PDU. It has a destination, okay, a DSAP, which identifies the high-level protocol that the data in the frame is intended for. So that would be right here, our first byte. Destination Service Access Point, DSAP. Okay, so what's our high-level protocol, basically? That's what this says. After a source service access point, right after that, and some controlled data. The actual user data follows the LLC field. Okay. Actually, it's pretty simple, but I want to know what the fuck the SSAP is because they don't seem to, like, we have a destination something and a source something. So, okay. Um, yeah, I don't totally understand what that source is for, but maybe I should. Maybe it's common sense. Given that TCP/IP uses the type field in Ethernet frames, there's very little use of the IEEE LLC encapsulation on Ethernet systems. Okay. So, we're not going to see this very much, but we're still going over it because it's a feature of Ethernet. May I offer a suggestion when explaining or tooltipping things? I don't know what tooltipping means, but you're always welcome to give suggestions. I'll just choose whether or not I listen to you. I'm also just, if you're new to this chat, just know that like I'm literally reading out of a book for my own edification. So this is me like studying in front of you. It's, how do I put this nicely? It's, I love interacting with people. I love that you come on and chat with me, but ultimately like this is for my edification, and if it helps other people in at the same time, then that is awesome. But if you're going to tell me how to run my stream, don't bother. Okay. But if you are here because you're an expert and you know things that I don't, then please throw them into chat and I'll read them out loud because that is cool. I do want to learn. Okay, cool. Well, then welcome to the stream. Glad to have you, Dr. Professor SC. South Carolina, maybe. I don't know. Okay, next paragraph. Here we go. When network protocol software uses the 802.2 LLC fields, multiplexing and demultiplexing work the same way they do for a frame with a type field. The difference is that the identification of the type of high-level protocol data is shifted to the DSAP, which is located in the LLC PDU. The whole LLC PDU fits inside the first 2 bytes of the data field of the Ethernet frame. So it's a lot smaller. In frames carrying LLC fields, the actual amount of high-level protocol data that can be carried is a few bytes less than in frames that use a type field. Wait. So even though it seems like it's small, because because all that stuff is just like in the data field, so it is taking up room in the data field. Hey, how's it going? Sharmaji, welcome. Lots of first timers today. It's good to see you. I was inspired by Trackapacer. God damn it. I can't even say Packet Tracer normally anymore. I was inspired by Packet Tracer. Yes. Yes, indeed. That is where my name came from. You may be wondering why the IEEE went to all the trouble of defining that 802.2 LLC protocol to provide multiplexing when the type field seems to be able to do the job just as well. The reason is that the IEEE 802 committee was created to standardize a set of LAN technologies and not just the 802.3 Ethernet system. To do that, they needed something that would work no matter which LAN technology was in use. Because there was no guarantee that all LAN frames would have a type field, the IEEE 802 committee provided the LLC protocol as a method of identifying the type of data being carried by the frame. All LAN systems have a data field, so it's easy enough to write network protocol software that can look at the first few bytes of data in the data field and then interpret that data in terms of the LLC specifications. All right, that's it. I'm gonna write my my own competitor for Ethernet. Competitor to Ethernet? Yeah, something that can compete with Ethernet. Which is nothing. I don't think anything can compete with Ethernet at this point. It would have to like shit rainbows and cause world peace or something in order to compete with Ethernet. Okay. I like I like the beginning of this sentence, of course. Just to make things more interesting, the 802.2 LLC protocol can also be used to carry the original Ethernet type identifiers. In other words, when you send a frame on a non-Ethernet LAN technology that doesn't provide a type field in its frame, there's a way to use the LLC fields to provide a type identifier. The rationale for this approach comes from the fact that the LLC fields are not large. Given that limitation, the IEEE didn't want to use up the limited number of bits in the LLC fields to provide identifiers for older high-level protocol types. Instead, a method was created to preserve the existing set of high-level protocol type identifiers and reuse them in the IEEE LLC system. Interesting. I thought okay. This approach, known as LLC Subnetwork Access Protocol or SNAP encapsulation, provides yet another set of bytes in the data field of the frame. The contents of the LLC fields of the frame are used to identify another set of bits in the data field, organized according to the SNAP specification, and the SNAP fields are used to carry the older protocol type identifiers. The standard for the use of SNAP encapsulation via IP is documented in RFC 1042. I won't go there, but it would be interesting to read on the side for sure. So this kind of seems to me like tunneling, or no, like encapsulating, which is not the same as tunneling, encapsulating Ethernet data, Ethernet type stuff inside of another LAN technology, as long as it follows this standard. Which is interesting. I don't know right off why you would ever do that, but cool. Because yeah, it can also be used to carry the original Ethernet type identifiers. So LLC can be an alternative to the Ethernet type identifiers. It can also carry them, though. So it's kind of neat. Oh God, sorry. Dr. Professor's yelling at me. Serial can compete. You can't make Ethernet interesting until you get to HDMI over Ethernet. Okay, shit. I forgot all about Serial. I know next to nothing about Serial, so, you know. USB is Serial. USB over TCP IP. At some point, unless I have diagrams of like what the frame looks like, my brain melts. But cool. Okay. Snap encapsulation. Okay, if you're writing network protocol software, then snap encapsulation is a handy way to continue using the same high-level protocol type identifiers when sending frames over other LAN systems. In the Ethernet system itself, of course, TCP IP. Oh, sorry. You ever like have to burp and yawn at the same time? What is that? Why? Okay. Starting over. If you're writing network protocol software, then snap encapsulation is a handy way to continue using the same high-level protocol type identifiers when sending frames over other LAN systems. In the Ethernet system itself, of course, TCP/IP protocol software simply uses the type field. And you don't need to concern yourself with any of this. However, you'll probably encounter snap encapsulation if you deal with multiple LAN systems at this level of detail. Okay. As a network user, you don't need to lose sleep over which frame format your computers may be using. Why not? I'd like to. The choice of frame format is built into your networking software, and there's nothing you need to know about it. Sorry, there's nothing you need to do about it. What if I want to fuck around with it? Okay, that's how that's how chapter 4 ends. They're just like, here's all this like fucking information, but you don't need to give a shit. All right, we're done. On to auto negotiation. Oh man. This is not okay. I beg to differ. This is not a shit book. I don't know. I've never read a book about Ethernet until now, so maybe it is. It's O'Reilly. It has an octopus on the front, which is really cool. Yeah, see here, I'll show you. A minute. Zoom out. Usually I start with it on, yep, there he is. There's the octopus. Ethernet, the definitive guide, 2nd edition. Yeah. He's pretty intimidating. He's appropriate though for a networking book. All right, back to 5. We are still in part 1, Introduction to the Ethernet, and there are 5 parts to the book. I'm never going to finish it. Okay, here we go. We'll try and get through a pretty good chunk of auto negotiation, but I have 2 hours set aside for the stream in case I feel like it, but you know, I'm gonna have to maybe stream a little more often, get my voice used to it, because at some point my throat just doesn't want to let me talk anymore. I keep drinking water. Okay. Auto negotiation. Automatic configuration of Ethernet interfaces over twisted pair links and one fiber optic media type is provided by the auto negotiation protocol. Auto negotiation is defined in Clause 28 of the Ethernet standard for twisted pair links and Clause 37 for 1000 base X fiber optic link. The auto negotiation system ensures that devices at each end of the link can automatically negotiate their configuration to the highest set of common capabilities. Thank you for subbing, Dr. Professor. Wait. Have you written a textbook, Dr. Professor? Because if you have, I'm gonna look it up. I'd like to know. Do it. Tell us. You only have 11 people watching this. It'll be fine. Dox yourself. Okay. Oh, man. Okay. He's not gonna dox himself. I'm sorry, I'm assuming you're a man because just most people I run into in network engineering are men, and I need to stop that. Okay, what did I just read? All right, so as a preface, actually, to me maybe going bananas during this chapter on auto negotiation, I've had this ongoing like a very heated discussion about auto negotiation on Twitter. It's taken a break. It's taken a bit of a backseat lately, but it's been really fun every time I bring it up because yeah, I can't go into specifics, but for some reason or another, I'm more or less aware that like you don't have to have auto negotiation happening like enabled at all in order for 1000 base T, specifically 1000 base T to work. As long as both sides are not using it, right? But a lot of people a lot of people are under the impression that clause 28 actually says you have to be using auto negotiation with 1000 base T, 1 gig copper Ethernet, right? You don't. Because what it says is you have to support it. You don't have to use it, right? It's very like mincy words. Anyway, I'm not going to take credit for like realizing that. Somebody else told me that, and it's just like been a really interesting thing to think about and talk about and yell about and lose sleep over. um so anyway, and you know, the whole thing is like, all right, at the end of the day, it boils down to like, why the fuck would you ever not use auto negotiation? And there are reasons. Like there are some use cases, right? Probably not commercial uses, or like very common things at the moment, but there are reasons you may not want auto negotiation. Cat 6 works for most up to 100 meters at 10 gig. Yeah, Cat 6 is good. Cat 6 knows what it's doing. The 6th cat. All right, here we go. A separate auto negotiation system was developed for use with backplane Ethernet technology, which is defined in Clause 73 of the standard. How many fucking clauses does 802.3 have? Holy shit. Hang on. Nope. Yeah, whatever. Okay. The need for automatic configuration system for Ethernet links becomes obvious once you understand that in order to correctly connect a desktop computer to an Ethernet switch port, for example, you must know the speed at which the Ethernet desktop interface and switch port should be set to operate. Excuse me. And whether full duplex mode is supported on the devices at both ends of the link, and it should therefore be enabled. However, features like the speed and duplex settings are embedded in the network equipment and they're invisible to you. I had an issue recently. I installed ESXi on just like some PC that I had lying around, like assuming that it was gonna work. I don't know what's in the PC. Like there's a motherboard in there and like a CPU. There's something. I don't even know what I'm saying. There's something in there. It works. I installed Ubuntu on it prior to that and could get to the internet and everything using Ubuntu and everything. So it works, but I installed ESXi on it and there's something fucking weird happening. The ports, like, I've connected it directly to the router, connected it to a Ubiquiti switch, like and a net, no, what was it? It was like a Netgear switch, not Ubiquiti. And it just doesn't, the ports don't want to come up. And you go into like the CLI, the ESX CLI, and you can see that the ports are in half duplex speed 0. So I manually changed them. I tried everything. I tried like what you would want, speed 1000, full duplex, and it looked like I tried auto negotiation too, and nothing worked. In the end, like it would change it to that and say it was that for like 5 seconds while the link tried to negotiate that, I guess, tried to work, and the link didn't come up, so it would go back down to half duplex speed 0. Super frustrating. I went through all this troubleshooting, worked with several different people who know a lot more about ESXi than I do. Nothing brought it up. Nothing. Fucking insane. I tried different Ethernet cables. And like I said, I was able to, on the same machine without any physical changes, I was able to reach the internet just fine with Ubuntu. So obviously, like, ports were good, everything was coming up. So, like, any kind of physical defects, I think were proved out that way. So I think it's like a weird ESXi thing, or maybe the hardware I'm using actually isn't compatible with ESXi, but I'm really sad about it because that was like, I used up all my motivation to like try and start a home lab with that, and it's just gone now because it like fucking didn't work. I'm gonna have to like, wipe the whole thing and start over maybe if I want to, but it's a lot. A driver. What did you install Ubuntu to? Oh, I'm sorry. I installed Ubuntu just straight onto the machine. I didn't install it to ESXi because I can't fucking get, like, ESXi I was able to get to work, right? Like it installed properly, but then, I set the static IP. I did everything, I did everything right that you're supposed to do, right? I gave it a static IP that was on the same subnet as the machine I was trying to manage it from, like all the good stuff. I even got on the router I connected it to and like tried to manually, like I had I had like one hand on the keyboard on my personal PC and one hand on the keyboard of the ESXi machine, and like was like forcing 1000 full duplex at the same time, and nothing, it didn't fucking work. It was so weird. Nobody knows what my issue is. I talked to several different people who are like networking experts, way more knowledgeable about ESXi than I am, and it just, no one could figure it out. So I'm pretty sure it's just like some weird hardware incompatibility. Because the ESXi, like, it should have, it installed fine. I would have thought maybe it would give me like a warning or error or something if maybe the hardware wasn't compatible, but it didn't give me anything like that. So I don't know. Mm. Oh, I see. Okay. Watch out for the ESXi hardware compatibility gotchas. Yeah, at this point, that has to be what it is, right? Because I proved out any cable issues. I mean, when I was just using it as a straight up Linux machine, like it was working fine and connecting to the internet just fine. So that's what I fucking get, right? For trying to like one weekend set up something for home lab. Anyway, all right, that's no I've gotten way off topic. We're talking about auto negotiation of links. You run Steam VR and ESXi? Sick. Yeah, I probably need to just, I don't know. I don't really want to install ESXi on my personal PC or on my like gaming PC. I don't know. Not that that's what you're doing. Sorry. I was just thinking about like what alternatives I can do. I'm gonna have to buy a fucking server. I don't want to. I don't want to buy hardware just to. Maybe I'll use AWS or something for my home lab. I don't know. I gotta learn. Speaking of which, I'm studying for AWS. I need to focus. We're focusing. Talk about this later. Oh my god. All right, so we talked about connecting desktop computer. You need to know the settings or else you're fucked. Okay, one RJ45 twisted pair Ethernet port looks a lot like another, and it's not obvious which network options may be supported by the equipment connected to that port. Auto negotiation allows Ethernet equipment to automatically detect and select the correct speed, duplex, and other features, thus relieving you of this configuration task, while ensuring that the Ethernet connection provides the maximum performance supported by the equipment involved in the connection. Excuse me. Okay, yeah, we all know that. The first part of this chapter, I'm not going to read this. It's just telling us how we're going to learn. I don't give a fuck. Let's dive in. Development of auto negotiation. Yeah, history lesson again. All right, the specifications for twisted pair auto negotiation are defined in Clause 28 of the IEEE standard, first published in 1995 as part of the 802.3U Fast Ethernet Supplement. Okay, that's maybe I expected later than that, but no, that's cool. So they came up with this pretty quick. Well, pretty quick. Ethernet happened in the 80s, right? So anyway, this portion of the standard is sometimes described as 802.3U auto negotiation. The auto negotiation specifications were based on an automatic configuration system called N-Way. Now we get to learn about N-Way. Okay. N-Way was originally developed in the early 1990s by National Semiconductor for use in its ISO Ethernet system. And then for some reason, we're like taking this to a little lemur sidebar here. It's token ring. You shut your mouth. I don't want to hear about token ring. The ISO Ethernet system was designed to provide both a 10 megabit per second Ethernet signal and a separate 6 megahertz isochronous, another amazing word. I assume you say it isochronous, but now that I'm saying it, it sounds kind of stupid. So maybe that's not how you're. Shit, I'm gonna look this up. I don't want to keep saying the word and have it. What a cool word, though. Seriously, isochronous. Isochronous. Hang on. Hang on. Pause the stream. Listen to this.
Isochronous.
Isochronous. Damn. I should have known too. I should have known. Okay, it's isochronous. Anyway. The ISO Ethernet system, designed to provide both a 10 megabit per second Ethernet signal and a separate 6 megahertz isochronous channel that could be used to carry voice and video services. Uh, you know, you know what I didn't do when I was looking up how to pronounce it? Was look up what the fuck it means. I think I know, like from context clues, but I want to know like 100%. Okay, simultaneous. It's the same thing as simultaneous, like occurring at the same time. Cool. Isochronous networking was designed to support applications like digital voice or video transmission that have strict timing limits that must be met. An isochronous data channel is designed to provide guaranteed bandwidth and signal jitter bounds for a service, permitting data to flow at the rate needed to provide voice or video without audio dropouts or missing portions of video. Oh yeah, Dr. Professor, you knew. Isynchronous? But it's not spelled sync, it's spelled isochronous. Do you really say isynchronous? Dr. Professor's drunk talking about network engineering. No other good way to do it though. Hang on. What the fuck was I just talking about? Isochronous. Okay, N-Way. That's where it came from. N-Way developed in the 90s for use in its ISO Ethernet system, which was designed to provide a 10 megabit per second Ethernet signal and separate 6 megahertz isochronous channel to carry voice and video. Guaranteed bandwidth and signal jitter bounds for a service, yada yada yada. Okay, so primitive quality of service, perhaps ish, maybe. The N-Way auto negotiation system was developed to discover whether the equipment connected to a given twisted pair ISO Ethernet link could support isochronous services. I'll never get over this word. And I've lost my way again. N-Way auto negotiation was developed to discover whether the equipment connected to a given twisted pair ISO Ethernet link could support isochronous services and enable those services when available. The ISO Ethernet system and N-Way auto negotiation became standardized as the IEEE 802.9 Integrated Services LAN standard. Although the 802.9 standard was not a commercial success, the N-Way auto negotiation system was later adopted by IEEE 802.3 to provide automatic negotiation of Ethernet capabilities. So wait, we have a standard that's 802.9 and then it turns into, it gets cannibalized by 802.3? Is that what's going on? I didn't realize that could happen. Maybe I should have because we got a whole history lesson at the beginning of this book, but whatever. When higher speed 1000 base T and 10 gigabase G base, do you pronounce it G base or gigabase? Gig base? 10 gig base T. That sounds right. 10 gig base T. Blah, blah. Okay, when higher speed Ethernet systems for twisted pair media were developed, they were designed to also use. See, here it is. Here's the spicy topic. They were designed to also use Clause 28 auto negotiation, so that Clause 28 auto negotiation signals work across all twisted pair Ethernet median types, including the 10 base T, 100 base TX, 1000 base T, and 10 gigabase T media systems. I'm pretty sure that if this book were like revised for 2022 instead of like 2006, which I think is this version, I have the latest version of this book, second edition, and it's from like 2006, so yikes. Okay, what the fuck? Okay, yeah, so including basically all these fast ones, like auto negotiation, all these faster ones were designed to work with auto negotiation, because why the fuck wouldn't you use it, right? Asynchronous. But it's spelled isochronous. Like sync, it's not spelled S-I or S-Y-N. There's no like N. It's ISOCHRONOUS. So there's no there's no like sound in that second syllable. You're wrong. I'm very sorry. I'm very sorry. Yeah, okay. 10G base T. Oh, 10G base T. 10 gigabit base T or 10G base T. 10G base T rolls off the tongue much better. Thank you, Cisco Tech. Woo! All right, here we go. Fiber optic. Auto negotiation for fiber optic media segments turned out to be sufficiently difficult to achieve that most Ethernet fiber optic segments don't support auto negotiation. During the development of the auto negotiation standard, attempts were made to develop a system of auto negotiation signaling that would work on the 10 base FL and 100 base FX fiber optic media systems. However, these two media systems use different wavelengths of light and different signal timing, and it was not possible to come up with an auto negotiation signaling standard that would work on both. That's why there's no IEEE standard auto negotiation support for these fiber optic link segments. The same issues apply to 10 gigabit Ethernet segments, so there's no auto negotiation system for fiber optic 10 gig Ethernet media segments either. Is this still true today? Because once again, this book is from 2000, year of our Lord 2006. It's like 20 years ago. The 1000 base X gigabit Ethernet standard, on the other hand, uses identical signal encoding on the three media systems defined in 1000 base X. I feel like that's a typo. It uses identical signal encoding on media systems defined in it. Maybe it's just awkwardly worded. Anyway, this made it possible to develop an auto negotiation system for 1000 base X media types as defined in clause 37 of 802.3 standard. The 1000 base X auto negotiation system is described later in this chapter. This lack of auto negotiation on most fiber optic segments is not a major problem. Okay, someone who's an expert, please tell me if that's still an issue today. I'm super curious. Given that lack of auto negotiation on fiber optic segments is not a major problem, given that auto negotiation is not as useful on fiber optic segments as it is on twisted pair desktop connections. For one thing, fiber optic segments are most often used as network backbone links. Okay, that makes sense. Where the longer segment links supported by fiber optic media are most effective. Compared to the number of desktop connections, there are far fewer backbone links in most networks. Further, an installer working on the backbone of the network can be expected to know which fiber optic media type is being connected and how it should be configured. Cool. Oh, okay. 2014, if this is the second edition. All right, I could be wrong. I swear to God, I thought I had looked it up and it was from 2006. But now I want to look it up. You might be right though. You might be right. It might be the first edition I'm thinking of that's from 06. That might be it. Actually, what am I talking about? I don't have to Google this. What page are we on? 65? All right. Boop, boop. Where is it? Yeah, you're right. 2014. Thanks, Ian. NetEng Ian. Okay, so I was wrong. So this is Year of Our Lord 2014. Much better than 2006, but still not great. But closer to a decade old than 20 years old. Boop. Nope. Where are we? Nope. Nope. Close. There we go. All right, basic concepts of auto negotiation. All right, 15 more minutes and the stream is kaput. The auto negotiation system makes it possible for Ethernet stations to exchange information about their capabilities over a link segment. This in turn allows the stations to perform automatic configuration to achieve the best possible mode of operation over that link. At a minimum, auto negotiation can provide automatic speed matching for Ethernet devices at each end of a twisted pair link. By using this mechanism, an Ethernet-equipped computer can automatically take advantage of the highest speed offered by a multi-speed Ethernet switchboard. The auto negotiation standard includes automatic detection of more than just the speeds of the interfaces at each end of the link. An Ethernet switch capable of supporting full duplex operation on its ports can advertise that fact using auto negotiation. If a station that also supports full duplex operation is connected to the switch, then the station and the switchboard can automatically configure themselves to use the full duplex mode over the link. However, the auto negotiation system does not perform any cable tests, such as detection of the number of wire pairs or any signal performance tests. Auto negotiation was designed to be extensible and to support the negotiation and configuration of multiple modes of operation and other Ethernet features. Automatic configuration makes it possible for vendors to build twisted pair Ethernet interfaces that can automatically support several speeds, so that Ethernet switches now support multiple Ethernet speeds on their twisted pair ports, as do the twisted pair network interfaces in computers. Depending on the cost of a switch, switch ports may support either 10 100 or 10,000 megabit per second operation. If a switch port supports 10 gig Ethernet, then it typically will support 100, 1,000, 10,000 megabit per second operation. Operation of the auto negotiation system includes the following basic concepts. Oh, goodness. Okay. Auto negotiation operates over link segments. Auto negotiation is designed to work only over a link segment media system. A link segment can only have 2 devices connect to it, one at each end. Okay. So link segment, point A, point B, boop. Auto negotiation occurs at link initialization. When a device is turned on or an Ethernet cable is connected, the link is initialized by the Ethernet devices at each end of the link. Auto negotiation and link initialization occur only once prior to any data being sent over the link. Once the link characteristics are set, they remain the same as long as the link is up. Twisted pair auto negotiation uses its own signaling system. Okay. Although each twisted pair Ethernet media system has a particular method of sending signals over the cable, thanks for subbing, Ian. Woo! The twisted pair auto negotiation system uses its own independent signaling system designed to operate over any twisted pair cabling that can be used to support Ethernet. It's cool. If auto negotiation cannot establish a common mode of operation, the link won't come up. If there's no common technology detected at each end of the link, then the auto negotiation protocol will not allow communications. In this case, the switch port or network interface card, I hate when they do that. I'm just like in a groove reading and like thinking, and then they throw me for a loop with fucking, do you ever need to, this is like the 20,000th time in this book that they've written out the words network interface card and then put in parentheses after it Nick. Like, just put Nick in there. I don't want to read the whole thing every time. All right, I'm done. Okay, so if there's no common technology detected at each end of the link, then auto negotiation won't allow communications, and the switch port or NIC port will not be functional. This is the same situation that occurs when 2 incompatible Ethernet devices that don't support auto negotiation are connected over a link. The 2 different systems can't communicate and the link won't come up. All in the comments are funny. When describing the operation of auto negotiation, the device at the opposite end of a link from a local device is called the link partner. Using the auto negotiation protocol, each device advertises its capabilities to the link partner at the other end of the link. This is something that I found so interesting. Like, as a network engineer, I thought auto negotiation was very simple. Which, I mean, it's not super complex, but like, okay, I got my CCNA. I was like, all right, cool, auto negotiation, done, got it. I never knew that there's advertisement in auto negotiation, right? If I had thought about it for like 5 minutes, maybe I would have like understood that. But yeah, you just kind of take it for granted. A lot of the Ethernet stuff that happens, all the stuff that happens with Ethernet, you take it for granted. And I just find it very interesting that there are actual advertisements with auto negotiation. Okay. Using the auto negotiation protocol, each device advertises its capabilities to the link partner at the other end of the link. The protocol then selects the highest common denominator between the devices at each end of the link. Okay, and then of course we have a figure we can't see yet, but each link segment has 2 devices, a computer and Ethernet switch port. Let's assume that computer A only supports 10/100 operation and computer B only supports 1,000 base T. Let's further assume that all the ports on the Ethernet switch can support 10, 100, and 1,000 base T. With auto negotiation, both computers can automatically configure themselves for the highest performance possible over their respective links to the Ethernet switch. Okay. Boop, 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 boop. When will auto negotiation end? Time is up. Gotta end soon. Okay. The auto negotiation communication method for twisted pair Ethernet is based on the link integrity test pulse, which was first developed for use in the 10 base T media system. The 10 base T link pulse was designed to protect a 10 megabit per second twisted pair Ethernet link segment from an undetected failure in the two pairs of wires used to carry signals over the segment. To help the Ethernet device at each end of the link avoid the problem of an undetected failure, 10 base T transceivers transmit link pulses when there is no data being transmitted. This is also very interesting, very good to know, and pretty cool. Continuous reception of either a data signal or a link pulse assures the interfaces at each end of the link that the link is working correctly. So Ethernet does have keep alives. Pretty neat. Y'all in the comments. Okay. The signaling methods used in faster Ethernet systems result in a continual stream of signals even when there's no data being sent, which means that the link pulse used in the 10 megabit per second system is not needed to detect a link failure on the faster systems. The auto negotiation system uses a burst of the normal link pulse or NLP signal, which is called a fast link pulse or FLP. What? Hang on. We use an NLP, which is actually a fast LP, or a burst of normal link pulse. I don't remember normal link pulse, so either they haven't talked about it yet and this is just a throw-in, or I've completely forgotten. Both things are equally likely to have happened. Okay, a burst of this, regular signal that's sent over it. Auto negotiation uses a burst of it, and so it's faster, I guess, so it's a fast link pulse. FLP signals are used to carry auto negotiation information between the devices at each end of the twisted pair link. The auto negotiation FLP signals are specified for transmission over the set of Ethernet twisted pair media systems, including 10 base T, 100 base TX, 100 base T4, 100 base T2, 1000 base T, and 10 gigabase T. Of these media types, the 10 base T, 100 base TX, and 1000 base T systems are very widely used. 10G base T system is often used in data centers and other environments that require high speed performance. Equipment based on the 100 base T2 standard was never built or sold, and although a 100 base T4 equipment made it into the marketplace, it too is no longer sold and is rarely found in use. Pretty cool. Okay, I'm gonna stop here because my voice is getting kind of scratchy. And we've done a pretty good amount of stuff. I'll try to remember we're at basic concepts of auto negotiation. We're talking about FLP burst operation in the next stream. Thank you for joining me on this journey into Ethernet. Dr. Professor, thank you. Nice to meet you as well. I'll see you later. I stream regularly on Monday nights at the moment, so please join me. Yeah, I have it set normally. My schedule is now starting at 7 o'clock PST in the evening, which I know is a little bit late for people in Eastern time zone, let alone like across the world. So I'm very sorry. I'm in the worst time zone ever, but I had to do it. I had to move here. So anyway, join me if you can. Love to have people chatting. And again, if you know more about whatever I'm talking about than I do, which is probably everyone, I would love to have you join and school me on it, because it's always good to learn. So you can find me on Twitter at Trackapacer and YouTube as well, where I upload the recordings of my streams after the fact. So anyway, thank you for joining me. I love you. Have a good night, morning, afternoon, whatever it is.